Hello guys, welcome to our today's talk regarding malware development for advanced adversary emulation. And my name is Pavel Kordos, and today with my friend Patryk, we'll try to introduce you into a world of malware development. I work as a penetration tester, also as a red teamer. Patryk, one word from you.
Hello everyone, so my name is Patryk Czeczko. I work as a technical director in a purple team in a global bank, and previously I worked with Pavel in a big four company.
Yeah. So actually, we've been working together for a couple of years, and during this time we've performed hundreds of engagements, during which we engaged some knowledge we'd like to share with you today. And I think it will be useful during both red teaming and maybe purple teaming activities, depends on what you are doing. And also, if you are a part of a blue team, I think it's great to know how actually malware works, because this may actually really expand your knowledge regarding the attacker's technique. All right. So let's start from the beginning. Today we will talk about a few different aspects. So first we'll start from malware preventions and detections, understand how actually antivirus and EDRs works. This is crucial to a proper malware development, because without knowing that, you don't know who are you on what were you dealing with. And we'll try to understand how malware analysis is performed. Then Patryk will tell more about malware delivery, how malware is delivered, then covers loader architecture overview, and some malicious loader things like bypassing static Iocs, antivirus and sandbox evasion, and some kind of obfuscation techniques. Hope you will find that useful, and maybe we can begin. Alright, so the first part is to understand who is or what is the antivirus and how they actually work. So there are a couple of different ways how actually antivirus solution works. And the first one is this very simple, the signature-based detection, which actually check your file and your things versus a list of known files which they are known for being malicious. This is a very trivial one. Also, this signature-based detection consists of known strings detection, like malicious strings within your application, and no byte sequences. This is very trivial to perform by antivirus solutions. But if something is really trivial to detect, probably something will be very trivial to actually fool the antivirus solution, which we'll show you in a few minutes. Then we got something a little smarter. This is called Heuristic Detection, and this actually performs a static analysis of the application behavior and identify potentially malicious characteristics and functions within this application. Those two things are like the base for most of the antivirus solutions. And something more dynamic one is sandboxing. This actually applies to most solutions. There's a sandbox environment which provides you controlled environment for the antivirus to actually launch the file and actually execute it, monitor the actions, and by doing that, it can actually observe the application's behavior. And it's very useful to know, to understand that, and if you know and understand what are the artifacts for this sandbox, you probably will be able to skip that. And there are some also EDR specific, Patryk, right?
Yes, sure. So in the era of endpoint detection and response, we get more and more, for example, function hooking. So that's some clever technique used by defensive solutions to trick malware, but we can bypass that. And there's also memory scanning performed here and then, but it's more difficult to bypass, but still possible to do something about that from malware developer's perspective.
Alright, and so how this malware analysis is performed. First, there we got, as before told, the static analysis. Those are the informations also included in the PE file, source code recovery, and source code analysis. This is relatively easy to perform also for malware analysis, because keep in mind that on one hand you are facing some kind of fancy antivirus solutions, but also there are some malware analysts which probably will be taking a closer look into our file, and we definitely don't want to make their job easier and eventually have our solution flagged. So don't forget about it, and there are some couple of dedicated techniques also to make their life a little harder. Alright, static analysis is one thing, then we got this dynamic analysis, which consists of this execution flow analysis, monitoring and checking system API calls, some kind of file system and registry changes. This also applies to network traffic, because this one is also performed. Lastly, we got debugging, which consists of step-by-step execution and modifying the program and at the runtime. Alright, so very basic one about the antivirus solution, but the very first step in each exploitation and in each malware creation, after malware creation, is actually the delivery. Delivery, a very crucial step, because the file has to be somehow on our victim machine, right?
Sure, so that's the first step of delivering. First step of the kill chain is actually the delivery of some malicious file, and we like to develop stuff in C because it's more difficult to reverse engineer by an analyst, and also gives like direct access to Windows API and all the functions. But there are some ways to deliver this code and execute this. So the most popular stuff is still, since 20 years ago I think or more, Office and Visual Basic for applications, so VBA macros. But there are also a lot of other techniques to execute some malicious stuff from Office documents, like old XR4 macros, dynamic data exchange, symbolic links. Those are called silk files. XLL, it's some Excel feature, also can be used for code execution. Object linking and embedding, so we can embed some objects into the documents. And also there's some cool trick with mouse over event in PowerPoint, so this can be also used to execute stuff. And another typical malicious document is HTML application, called HTA in short, and this can be used to run either Visual Basic script or JScript. And JScript is some language similar to JavaScript but used by Microsoft. And there are other techniques like click once or links. Sometimes we can send links or some other files that are very small but can contain some one-liners to be executed.
One little side note, I think, which will be outside of scope of this presentation, but still, Office documents are very popular because, of course, it's very easy to convince user actually to launch this file, because people they ignore those macro alerts. This is one thing. But actually, the history knows that there are some antivirus solutions on the market which actually they just simply don't check the macros, right? We know such an examples. We won't quote that, of course, but yeah, there are some of that.
Yeah, we've seen such stuff.
So you can basically paste very trivial payload inside of the macro, and it simply won't be scanned by the well-known product. That's a nice hint. All right. Anyway, let's go further.
Sure. So about native code execution in those malicious documents. So for example, in VBA, we can just import Windows API functions. And this is example of create process function, and that's it. We could import those functions and, for example, inject shellcode, allocate memory, and execute stuff directly from Visual Basic macro in Word or Excel. For HTML applications, it works in a similar way. We can use some COM objects to register some external functions from DLLs. So, for example, those Windows API functions. And there's some other tricky way you can see below is to actually instantiate an Excel object and then execute some VBA macro with this. And for JScript in HTA, this is very similar to the previous one. We can also import some functions from the DLLs, and you may be wondering what's that in double quotes. So this is actually this is actually a signature of the function. So those letters mean specific parameters like pointer, integer, short, long, or whatever, and this is what the function returns. So this is some information about the function and expected parameters and what does it return. But there's also an option to execute .NET assembly via deserialization, and there are some two good tools for that, namely .NET to JScript and Gadget to JScript. And from .NET or PowerShell, we can also simply import API functions, define them, and execute. So this is called actually platform invoke, and it's a matter of cooperation from .NET with low-level system APIs. And some cool trick from old times when we want to leverage batch files for execution of some executable, we can use some tools like exe to bat or hexbat, whatever it's called, to just write a hex dump in this form, and then the batch file executed would retrieve the contents of the file and run this using this debug tool, which is present on all Windows systems, I guess. And also about the shellcode, because usually we transform our C program into some form of shellcode to be executed by injection, for example, from this VBA macro or from HTA document or wherever else. So what's this shellcode actually? So this is some piece of position independent code, so it can be executed wherever in the memory, and it has some cool, clever features to bootstrap itself in every location memory. So it uses some common structures like process environment block to locate needed functions and load libraries and execute stuff later. And it's also mainly used in binary exploitation. So, for example, when we have some buffer overflow or heap overflow, we can place some short shellcode to be executed when we take control of instruction pointer in the application exploited. And as mentioned, this is a good stuff for in-memory injections, for in-memory executions, and also shellcode provides like this perfect code reflection because it can modify itself. So this is used for some runtime decryption of shellcode. Particularly Zorin encoding is very popular in shellcodes, like those MSF Venom encoders. And for Windows shellcodes, as I mentioned, it just locates the process environment block in the memory, then it locates loader data, list of imported loaded DLLs, because every Windows process has kernel 32 DLL and anti-DLL loaded, and those libraries have some functions that are necessary to load additional modules, namely get proc address, load library, get module handle, and this can be used to load any other library and invoke any function needed. So, for example, load library could be used to load the socket library, and then the simple reverse shellcode uses create process with sockets created by WSA startup attached to standard input and output. So that's like this simple reverse shell from Meterpreter. And injecting shellcode, so this is some simple code to inject shellcode in memory. It's also written in C, so it uses those well-known functions which because of that are kind of malicious. So first the process would need to allocate memory, then write the shellcode in some newly allocated memory, minding the permissions, of course, because to write stuff we need read-write permission, and to execute we would need read-execute. But we can also allocate memory with execute read-write permission, so we can do everything. Write the shellcode and execute this, and then we can create thread pointing at our shellcode, or just cast the pointer to a function pointer and execute this in C. But this won't work if permissions are not executable for this specific memory page. So that's about shellcode, and let's do this theoretical exercise of developing a covert loader. So let's say we want to have a loader written in C, obfuscated as much as possible, and this would eventually load, for example, a Cobalt Strike beacon. So that's a typical approach we used during our red teaming exercises back in the days. So starting with this architecture, we got here what we mentioned 2 slides before. So firstly, the application would need to allocate memory, write the shellcode, and then trigger execution. But this is some trivial stuff and would probably get detected right away by some antivirus. So what we can modify here? First thing, we could encrypt the shellcode, or just encode this, or use Zor encryption, wherever, to just bypass those well-known signatures for shellcodes. And then this could be decrypted in memory and then written in specific buffer and executed. Next step would be to implement some sandbox checks to bypass any dynamic analysis, either automated in a sandbox or manual by an analyst. Then we can also implement some anti-debug checks, which could be, of course, easily then bypassed by the analyst, but it would give a little bit of struggle to the analyst to find them and bypass them. Well, actually, maybe not that much, because, for example, there's this plugin for x64 debugger called Silahide, which bypasses those simple anti-debug measures. So anyway, that's like a cat and mouse game, or whatever you call this.
Like the whole malware development, right? Because
Yeah.
it keeps developing, and the malware manufacturer, the antivirus manufacturers, they keeps you blocking. Also, you got this machine learning thing, which gives you actually a whole new level.
Or it should. Well, the whole IT security is some cat and mouse game, and red teaming, blue teaming, purple teaming, and everything. Well, anyway, what we could implement further is to obfuscate some data, like some IP addresses or some function names or anything that's visible in the binary. So good thing would be to obfuscate the code or decrypt this during runtime, so it won't be picked by simple analysis, for example with strings tool, which gives strings embedded in the executable. And then come some clever techniques for bypassing memory scanning. What we could do, for example, is to write the shellcode, execute this, but after some time get the shellcode removed from the memory by, for example, another thread, another worker thread, and then this could be replied and executed again, so the EDR, for example, would have less chances of detecting this malicious stuff in memory. While doing this, we could also implement some anti-debugging features to make the debugging harder for an analyst, and we will talk about those specifics later. Another thing, cool feature we could implement in our malware is cracking of decryption case, because as we mentioned, we could use some obfuscation or decryption during runtime for some sensitive data like shellcode or some function names or IP addresses or any other IOCs. But either the key could be present in the binary and used for decryption, or it could be cracked. So this would take some time. We would need to use some short key, so it won't be cracked like forever, but in few seconds or minutes. And then this key would be used to decrypt stuff in memory during during runtime. And another thing on top of that is to dynamically resolve function names, and we'll go to that further. So this would bypass those IOCs based on import address table. So to hide those malicious functions like virtual alloc, write process memory, create thread or create process from the import table. And also for the whole development process, we could implement some compile time obfuscation. So for example, we could have some use some templates in C++ to change the obfuscation every time the code is compiled, and also leverage some compiler obfuscation, for example with low-level virtual machine, to obfuscate stuff differently with every compilation. So with every compilation we will get, of course, a new checksums to bypass some trivial detections based on MD5 sums of the file, but also the binary would look differently, and would be stuff would be encrypted with some other key dynamically created during compilation. So that's some advanced stuff, but very cool and useful.
Alright, so the next topic would be bypassing static IOCs, and we got a couple of static properties which will be included within our malware code. First one is definitely the hash of the file, then some of the strings within our code, static signatures. Then something which is definitely very often forgotten are those debug informations with a PDB file, then some imported DLLs and other functions. And what actually can we do against that? So there are a couple of techniques. So the first one for the file hash would be the compilation. Then for the strings and static signatures, we can use XOR encryption just to hide it, and that's basically it. For hiding debug information, we can go into the linker settings and try to hide that. For the DLLs and imported functions, there's this technique called API hashing, which actually hide it from antivirus and from the analyst. So the first one is a file hash. So I think all of you guys probably know the file hash. Each time when you compile a file, you got a file, and once you made a new compilation, the file is simply changed. So the hash changes, and this is a very trivial technique. If you want to change the file hash, just simply try to recompile the code, and that's basically it. All right. So the next thing, which will be the PDB file. Well, what is actually a PDB? This is a program database file, often called as a symbol file, which stores some debugging information, and this file is generated when during the compilation to store just the debugging information. Of course, this file is not attached to some kind of executable file which will finally produce, but in your executable file, you will have a reference to this PDB file on your home directory or on your folder where your project is. So if an analyst or whoever will perform a very simple search through your through this file, he or she may find a reference to this to this PDB file. And finally, it can also somehow store kurwa. Okay. And finally, it can somehow expose some of your sensitive information, like your home directory or something which will be in this directory. So it's a very good practice just to change it in linker settings, so it won't be included, or the directory won't be included in the final executable file. All right, so the next one will be associated with hiding import and functions, API hashing, but I think this is your favorite one. So
yeah, that's cool stuff. So normally when we use some API functions, we would have this reference sorry, in the import table. So for example, when injecting shellcode, we would have references for those malicious functions in the import library, because Windows Loader needs to load those functions for the executable to work. But what can we do here? We could use mentioned functions like load library, get module handle, and get proc address, which are used by shellcode. We could leverage those functions to find any other functions dynamically during the runtime, during execution of our application, and then only functions visible in the import table will be those for loading external libraries, and at the first glance we would not see that the application actually imports this malicious create thread or virtual lock, virtual protect, or other functions like that. And we can take this further and implement this shellcode style bootstrapping in our application. So to hide those load library and get proc address, get module handle function from the import table, we could find all those functions dynamically in memory, just like the shellcode does. So the algorithm for this is to locate the process environment block, and this is simple as referencing to FS or GS register for 32 or 64-bit architecture respectively. And then there is this loader data structure in memory in the process environment block, which contains information about all loaded modules, either executable or DLLs. And then browsing through those informations, we can find actual names of functions for specific libraries, and then knowing that kernel 32 and anti-DLL are loaded for every process, we can browse the kernel 32 exported functions which addresses are located in memory to find them by name. So we could find those 2 or 3 functions to load external libraries and locate specific functions. And then after dynamically finding address of those functions, we could call them with arguments of other functions and load wherever we would need. So for using this shellcode-like technique, we would have actually empty import table. So everything would be found dynamically during the execution. And this is the code for that, so it's quite long, but you can find this and all of the other stuff on my blog, which I will link later in the presentation. And also, just checking the process environment block in debugger, we can see the information about loaded modules. So first module is the application executable itself, and then we have anti-DLL, kernel 32, and we can browse this to find specific function by names. And going further, because when we were looking for functions by names, we had to embed those names as strings in the executable. So still this could have been found by an analyst in the executable. We could, for example, encrypt or encode those function names, but other thing we can do is calculate hashes of those function names, and then while browsing every function For example, in kernel32 library, we could calculate a hash of the name, of the function name, and compare this with our predefined hash using some specific algorithm, and just find function that we need by hash. So like looking up something in the hash table.
Alright, and then the sandbox evasion. So if we can just place ourselves within the execution flow, right now we will try to skip the sandbox, which will be the sandbox check will be performed by antivirus. The antivirus will try to run our software or our malware and verify whether what we actually have is malicious, and then after that it will perform a scoring and finally decide malicious or not malicious. And there are a couple of these techniques which actually can fool the antivirus that the piece of software which actually run is not something malicious.
And one thing to note here, that this anti-sandbox measures can also help us combating dynamic analysis, because usually analysts use virtual machines to analyze malicious samples, so we can implement those sandbox checks to fool this dynamic analysis in virtual machine also.
Yeah, so there are a couple of artifacts which are in common between the antivirus and actually the, let's say, a real virtual machine of a malware analyst, if we can call it that way. But let's start from the antivirus. We will try to match them in a few minutes. So the first one, actually the antivirus solution, it cannot prepare you a very great prepared environment. This is somehow simplified. And the two things, the first thing is the lack of resources. So we can actually check how much the CPU cores of our processor have, and this will be the first artifact. And actually we can check how much memory available we have on our machine. And if the machine which runs our code do not match our requirements, let's say, then we will simply stop the execution flow, and the execution flow will not proceed. Just like I said before, the resources are limited, and so we can try to allocate some huge amount of memory. This will probably be pretty tough for the antivirus to allocate, let's say, 10 gigs of memory. So maybe antivirus will skip at this point, because this software could not allocate that much, and will stop analyzing our malware. Another cool technique is try to load some fake library. Why fake library? Because if we'll try to load some existing library, it also could be emulated. But if we will try to, let's say, load fake.dll, we are pretty much sure that such a library will not exist on any machine, or maybe on your it could, but not in most cases. And if this antivirus, this sandbox, will try to virtualize that and will provide this fake DLL, we will be pretty much sure that we are inside of a sandbox, and again we can actually stop execution. Like I said also before, those virtualized and sandbox environments, they are very simple one, and somehow they struggle to support multi-threading. So using multi-threading is also one of the very efficient technique to skip being detected in this stage. Or if you have some knowledge regarding your target, especially if you are performing some kind of spear phishing attack and you know exactly what, like, the computers are called on our victim's environment, we can check for your computer name if the pattern match our requirements. If not, we can also stop the execution. Even we can try to verify the username of a user which is running our malware. And sandboxes are known for using very simplified users like admin user or whatever. We can check for that, and we can also use the opposite technique. We can try if for example we are attacking John Doe, we can maybe verify if the user which launches our malware is actually a John Doe. This is also very cool stuff. And in most cases, you probably would be aiming a domain environment, so so it's also worth to check if our domain is domain joined. Regarding the USB devices, one funny fact is that we can actually see how what are the USB register values, and those virtual machines, they will probably won't have any history of mounted USB devices, so it's always great to have that. Of course, in some environments, like in bank environment, those USB devices may not be the greatest technique because USBs may be disabled, so just adjust it into your project. Just like Patryk said, there are some common artifacts between sandboxes and the virtual machines which belongs to a malware analyst, and probably both of them will be virtual. So as you probably know, if you have a virtual machine, we got these artifacts like guest additions for most or every single virtual tool, and we can try to see whether those files actually exist on the system, and we can also query the registry and see if we have the keys inside of our register. If so, we will be able to detect that we are within a virtual machine, which probably is not our target, and then we can also try to skip that. And speaking of which, when it comes to virtual network adapters, they have this MAC address which belongs to the vendor, like virtual like a VMware or Oracle. You can all check that. You can check the MAC address of this network device and the execution if we have something from a known list. And the clock is ticking. The clock is a really funny part, because it is not as easy as sleep 10,000, right? You cannot just sleep the code.
Yes, we could, but the clever sandboxes, like for example, properly configured Cuckoo sandbox, which can be used also for sandbox-like analysis, can just hook API functions and delay those sleeps. So we as malware developers would sleep our code for a few minutes to time out an automated analysis in Sandbox, but Sandbox could trick us and fast forward our delay and execute the code further. So what we could do, we can first of all use the lowest API, which is anti-delay execution, because sleep function eventually calls anti-delay execution from anti-DLL. We could sleep, for example, for 100 seconds and then measure time elapsed, before and after, and see if actually 100 seconds or so have passed, and if not, that probably means that the environment is monitored, hooked by some sandbox, for example, environment, and the sleep was fast forwarded. But also the get the count function, which returns the system time, it could be hooked and return false values in the sandbox. So what we could do with that, there is some system structure called kernel user shared data, and on specific offsets, these are like the same for every system, I think, we can check the information about elapsed time stored there, and that's read-only, only modifiable by kernel, and less probably tampered with by the sandbox. So I think it's the most reliable source of information for the system uptime. So we could use this to check if those 100 seconds that we should have slept have actually passed or not. And about hooking functions, why some environment like Sandbox or EDR would hook functions. So first thing mentioned, for example, to return false uptime or fast forward our sleeps, but also to monitor what we are doing in a system. So for example, those create thread functions or memory allocation functions, those crucial ones could be hooked, and when a malware invokes this function, the execution flow would be redirected to some EDR module, for example, and then parameters would be checked, and if for example the pointers, which are argument to the function, point to some malicious buffer in memory, this could be blocked by EDR. And the same case is for process dumping. So the lowest level API for reading memory is anti-read virtual memory, and the argument for this is the process name, I think. So the EDR or sandbox could, well, in this case EDR probably, because we're assuming that we are attacking some live, some actual environment of a user. This EDR would hook this function and check if we are trying to dump the LSA memory, and if so, just to deny the access, to stop the execution. And what we can do with this, so first thing, we could browse the actual assembly code of the functions in memory to see if first instructions are modified, because usually the first instructions in hooked function would be something like call or push and return to actually call some function in external module. And we could see if that's the case for the function code, or even better, we could try to load the DLL from disk and then compare the stuff from disk with the actual function code in memory to see if it's different. If it's different, the function is probably hooked. So you can see some source code for that, but also you can find this on my blog. So going further, we would unhook those hooked functions, so just replace the function code with original stuff, for example from the file on disk. So that way we could clear those EDR hooks. But we could also bypass this by issuing direct syscalls. So for example, we can see procmon information here. When our application calls the create thread function, we see the other APIs that called, and the lowest level is anti-create thread ex, which and this anti-create thread ex function is actually some simple wrapper to syscall. And I think most of anti-DLL functions are just syscalls, and syscall is a mean of transferring the execution to the kernel, so the kernel does what's needed, and the syscall actually is just putting some specific ID in register, and then issuing this processor instruction called syscall, and then execution gets forwarded to the kernel. So we could also implement those direct syscalls in our code in C. So in Visual Studio for 32-bit architecture, we could just put inline assembly in the code, but for 64-bit it's impossible, and we need to create and compile some assembly file, an external file, and then reference this function in our C code. So for example, here we have a syscall implemented in assembly with a specific syscall ID that's different, maybe different for every Windows version or even release, because those change often. And then reference this function with this modifier external C. So linker would find this function in this compiled assembly, and then we need to provide the signature of function, so to provide all the required parameters for this anti-create thread ex function, and then this would be executed in kernel and completely bypassing any function hooks put there by ADR or any other solution like that.
Yeah, so now we have the anti-debugging techniques, which are crucial when it comes to fighting with malware analysts. And we got two very simple options to detect that. First one is the is debugger present flag, and also there are some other flags and artifacts which are set if you are debugging some kind of file, and you can use that to break the application in case it is being debugged. But don't forget to disable those, especially if you are actually working on the malware, because you can block yourself, and that's very also important to do. And you can also dynamically detect breakpoints, right?
Yeah, so that's some clever technique implemented. So let's say we have some crucial function and we would want to check if it's debugged or not, if there's some software breakpoint in this function. So what we could do is first put some linker directives to not to inline this function, and after compiling this like that, we would have this crucial function, and right after this we would have another function. So we could calculate the checksum of all the bytes of the function, starting with here, so beginning of this crucial function, and ending here, because the beginning of next function is the end of this crucial function. So we could calculate bytes to see if they were changed in memory, because if there's some software breakpoint placed in this function, the specific opcode would be present and the checksum would be different here. So that's some cool feature. And another thing to play a little bit with malware analyst is to use some Windows API callbacks, because when an analyst debugs our code and steps by every single instruction, they can see what is executing after what. But using callbacks, we can, for example, call the read file function, read file x, and implement some callback which would be executed after the file read is completed, and we could transfer our malicious execution to this callback, so this won't be caught that easily by the analyst. And some advanced obfuscation now. So this is also a cool topic. First, consider how the actual compilation process works. So first we have this front end, which processes the source code and creates this intermediate representation, and then the optimization takes place, which works on the intermediate representation level to reduce code complexity but not to change the application algorithm, and then the backend translates this modified IR code to assembly or some bytecode. And here comes Obfuscator Llvm, which is open source fork of low-level virtual machine, and Llvm is some compiler infrastructure alternative, let's say, and this includes a well-known CLang compiler, which is actually a front end, and this obfuscation works on this intermediate representation level. So we mentioned before that the second step is optimization, so the IR code is simplified so it would execute quicker, and the obfuscation is kind of anti-optimization, so it's mangled and probably would take more time to execute, but it's also harder to read, so the assembly generated from the obfuscated intermediate representation is more difficult to read by an analyst, for example, while reverse engineering the C or C++ code. Actually, the actual assembly generated. So, going to some example, we have this simple app which gets the tick count and performs some basic arithmetic operations. And after disassembling with Ghidra, we can see this tree of execution, this execution graph, and we have three types of obfuscation in this Obfuscator Llvm framework. So first is instruction substitution. So here simple arithmetic instructions are replaced with more difficult one, which actually give the same output but more code, as we can see on the function graph here. The second thing is bogus control flow, and this works differently. This places some opaque predicates before a given function block. An opaque predicate is some piece of code that is evaluated during runtime, but to a predetermined value of true or false. So during compilation, we actually know that, for example, this single predicate would be evaluated to false, but it's calculated during runtime, and then based on the condition a jump is performed. So an analyst would need to step by this predicate and execute this to see if it produces true or false, but we during compilation time know that, for example, it's false, and that a single conditional jump would be taken to a specific branch and not the other. And third thing is control flow flattening. So consider some algorithm with specific steps, and then we destroy this sequence of instructions and place everything at the same level, and actually the execution is controlled by a switch statement with some control variables. So these control variables can tell the application which block should be executed after another. So this is some heavy obfuscation, and using this the function graph gets much more complicated than the one before the obfuscation.
Alright, that sounds pretty advanced. And as a last part for today, last but not least, I think we have other tricks and clever techniques which you can actually use in your code. The first one, parent process ID spoofing. Also, we encourage you to take a closer look at process protection. Then advanced data obfuscation, some kind of time-consuming operations, and also environmental keying. Alright, so the first one, parent ID spoofing. So if you create a new process, you can use actually one of the parameters to provide a process ID. So you can abuse the relation between inner child of the process. So on the left we have the regular process of Notepad, and on the right we have a process when the process ID was actually spoofed. So this is a really good one, pretty good against I think some kind of blue teams and any other monitoring tools. Another technique is data obfuscation. This is always useful when it comes to malware developing. You can either use the Windows default functions, but those can be hooked. But so it's always a good idea to run your own obfuscation tool for encoding and decoding. And also you can do not deliver the key, but you can, during the code execution, you can try to brute force the key, so it actually makes a little more mess inside of the code and makes it also harder to decompile and reverse engineer. And also it's time consuming. We could program some brute forcing of a key to take a few minutes, so for example timeout in sandbox analysis. Yeah, so always keep in mind regarding the power of the machine you're trying to force, because if the key would be too complicated, it may take too long to actually decrypt the key. And the last thing associated with the things we have told you today is the environmental keying. So making the code execution depending on some environmental things like a computer name on a target machine. So if they don't match, the code will simply not run. All right, so this was that's all which we have prepared for you today. We hope you had a great time watching us today. Apologies. I encourage you to visit Patryk's blog, because it's actually his property, where you can find a lot of more interesting articles regarding malware development and other offensive techniques. So thank you for watching from me.
Thanks, hope you enjoyed this, and as Pavel said, feel free to visit my blog and see more of stuff like this if you like this.
Okay, see you guys. Goodbye.
Bye.